For this problem, we examine a polynomial function. We're going to analyze the function through various parts, ultimately leading up to a graph of the function. Our polynomial function is g of x equals 2x cubed plus 5x squared minus 28x minus 15. The first thing we'd like to do is determine the maximum number of real zeros that the function may have. The maximum number of real zeros a polynomial function can have is equal to the degree of the function. We look at our function, we see this has a degree 3, so the maximum number of real zeros is n equal to 3. Next, we want to find bounds to the zeros for the function. First thing we're going to do is rewrite our function by factoring out a 2. Well, g of x is equal to 2 times x cubed plus 5 halves x squared minus 14x minus 15 halves. By factoring out the 2, we've got this reduced expression in parentheses that has a leading coefficient of 1. If we look at just this expression in parentheses, we'll have a sub 2 is equal to 5 halves, a sub 1 is equal to negative 14, and a sub 0 is equal to negative 15 halves. To find the bounds on the zeros, we need to find the maximum of 1 and the sum of the absolute value of the a's. So the absolute value of a sub 0 plus the absolute value of a sub 1 plus the absolute value of a sub 2. This will be the maximum of 1 and the sum of 15 halves plus 14 plus 5 halves. So we have the maximum of 1 and 24, which is equal to 24. We also need to find 1 plus the maximum of the absolute value of the a's. A sub 0, absolute value of a sub 1, and the absolute value of a sub 2. This will be 1 plus the maximum of 15 halves, 14, and 5 halves. So we get 1 plus 14, which is equal to 15. Now the smaller of these two numbers is 15. Well, that gives us our bound. Every 0 of g lies between negative 15 and 15. So negative 15 and 15 are the bounds on the zeros. Next, we're going to find the potential rational zeros for our function. To list the potential rational zeros, we need to look at our leading coefficient and our constant coefficient. We're going to have a sub 0, that's our constant, is equal to negative 15, and our leading coefficient, a sub 3, is equal to 2. To find the potential rational zeros, we first find the values for p, the integers p, that are factors of a sub 0. So we'll get p is plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Then we need integers q that are factors of our leading coefficient 2. So q will be plus or minus 1 and plus or minus 2. Now we form all possible ratios, p over q, to list our potential rational zeros. If we look at all possible ratios, we'll get this ratio p over q will be plus or minus 1/2, plus or minus 1, plus or minus 3 halves, plus or minus 5 halves, plus or minus 3, plus or minus 5, plus or minus 15 halves, and finally plus or minus 15. So if our function g has a rational zero, it must be one of these 16 that we've listed here. In part D, we're asked to determine the real zeros of g, and then factor g over the reals. We're going to use the fact that if g of r equals 0, then r is a 0 of g. So we're looking for values of r that will make our function equal to 0. If we get g of r equal to 0, we can use long division to reduce our polynomial and then start again on the reduced polynomial. We made, in part C, a list of potential rational zeros, so we can start with that list and look for some integers that might give us g equal to 0. For instance, we can start with g of 1. If we evaluate the function g at 1, we get negative 36. Since g of 1 is not equal to 0, 1 is not a 0 of the function. If we try our next integer, the next positive integer, g of 3, g of 3 will give us the value of 0. Since g of 3 equals 0, we know that r is equal to a 0. Now we're asked to determine all the real zeros for our function g. We want to determine the real zeros of g and then factor g over the reals. For this part, we're going to use the fact that if g of x is equal to 0, then x is a 0 of our function. In part C, we found a list of potential rational zeros. We can actually use that list of potential zeros and evaluate our function at each of those to see if we get 0. We're going to do that, but we want to do it methodically, but also the easiest possible way. So we'll start with integers. We'll actually start with the positive integers. So we'll do g of 1. 1 is our first positive potential rational zero. That's an integer. We do g of 1 and evaluate the function, we'll get negative 36. Since this is not equal to 0, we know that 1 is not a 0 of g. The next positive integer potential 0 is 3. If we evaluate g of 3, we get 0. Since g of 3 equals 0, we know 3 is a 0 of the function. Therefore, x minus 3 is a factor. Since we know x minus 3 is a factor of g, we can divide g by x minus 3 and get a reduced polynomial. To do that, we need to use long division. We're going to take x minus 3 and divide into 2x cubed plus 5x squared minus 28x minus 15. Look at 2x cubed, we need to multiply x by 2x squared to get 2x cubed. 2x squared times x is 2x cubed. 2x squared times negative 3 gives us minus 6x squared. We subtract that. 2x cubed minus 2x cubed is 0. 5x squared minus a negative 6x squared gives us 11x squared. Since the minus the negative makes it plus, we'll drop down our minus 28x. Say to get 11x squared, we need to multiply x by 11x. 11x times x is 11x squared. 11x times negative 3 is minus 33x. Again, we subtract. We do our subtraction, we'll end up with 5x. Drop down our negative 15. To get 5x, we need to multiply x by 5, so we'll have plus 5. 5 times x is 5x. 5 times negative 3 is negative 15. We subtract that, and we get a remainder of 0, which we should if x minus 3 is a factor.